Alrighty. Hello, everyone. Welcome to Big Data Europe. Also for me, my name is Floor Drees. I'm a staff developer advocate at Ivan. I'll be your host for the last two sessions of today and then also tomorrow in the cloud and streaming track. I'd love to encourage you to ask questions and take part and be curious. Let's start with Christopher Woodward's session, Machine Learning and Graph Databases for Better Recommendations. Chris is a developer relations engineer at ArangoDB, contributes to the Arango ML project, which helps simplify the storing and managing of metadata for machine learning experiments. I read this from my notes because there's no way I could have memorized this by heart. Anyway, in his session, Chris aims to show us how pairing machine learning with graph databases can improve the quality of recommendations and offer some insights into the challenges of turning machine learning models into products. So whenever you're ready, Chris, take it away.
Thank you. Yes, as you said, this is a talk on machine learning and graph databases for better recommendations. And as you said as well, my name is Chris Woodward, and I'm a developer relations engineer at ArangoDB. This sort of involves, for me, like on a day-to-day, participating in creating things like trainings for developers getting started with ArangoDB, as well as doing a lot of like internal development projects, which is kind of what we're looking at today is the result of one of those projects. We made what we call a Arango Flix, a sort of like movie streaming site, and I'll get into that a little bit more. But that's a really nice side effect of being a developer relations engineer is that you still can do development, but with the outcome of hopefully figuring out ways to make it easier for developers to get started with whatever you're working on. And she also mentioned on the Arango ML team, this is sort of our machine learning wing where we're building out features to help make doing machine learning with ArangoDB easier. And I'll get into what that means. It doesn't really mean doing machine learning in the graph databases, but it means how we can make these two things work together better. And if you'd like to follow up with me afterwards, I'll be sending these slides around as well. So there's a lot of links throughout here that hopefully you'll get some use out of. But you can also follow up with me directly either on Twitter. We have a community Slack channel as well, and I'm chris.arangodb on there. You can email me or even follow up on LinkedIn. So the agenda for today is we're going to take a look at that Arango Flix project. And then we'll take just a really brief intro into graph databases, just for anyone that isn't familiar. But if you aren't familiar and you kind of want to learn more, we, of course, have a ton of resources available through our website. And just in general, there's a lot of really valuable resources on getting started with graph databases. And I provide some links to those throughout as well. And then sort of the bulk of the talk will be on recommendations, taking a look at what a recommendation engine is and a couple of the popular techniques for generating recommendations. And then for the machine learning side, we'll take a look at ways that we did this with our demo project. There's a lot of notebooks that we link to here as well. So if you want to follow up and kind of like dive into these topics a little bit more, we actually have notebooks that you can run. These are Google Colab notebooks, so they don't require any sign up, and they even generate a temporary database for you. So everything through and through is just you can run it and start using it without signing up, and you can just focus on the actual topic. And then finally, we'll just take a look at how we combine these two things. How do we actually use graph databases with machine learning? And so this is a really quick demo here, or a quick overview, basically, of what Arango Flix is. This is a website that I actually developed. I don't claim to be the absolute best this is a JavaScript developer, but as one of the tasks that I have on the machine learning team, if we need a front end, I do have some front end experience, so I hop in there, and I had a lot of fun with this one. And so this was the goal here, to try and recreate sort of a movie streaming site with some of the basic features that you'd expect. The ability to sort using facets, so you can sort by user rating, genre, language, and then on the sort of middle or the right section here, you can actually switch between the recommendation methods. This is really our main objective. We want to be able to offer a view of doing all these different recommendation types. And the goal here is not to say this recommendation is better than that recommendation. It's more so really to point out all the different ways that you could potentially offer recommendations and sort of start getting an idea on the pros and cons of each. And we'll get into that more as we go throughout this. And then you can also switch between users. So sort of that like who's watching profile sort of thing. And then at the bottom here, you can actually expand this to get more information about the actual recommendation method itself. So what AQL query did we actually use to get this recommendation? A little bit more information about the concept itself, and then some resources. So this is links to things like the data set we used or a paper on that actual topic. And this is actually available through our cloud offering. So if you want, you can sign up for a free trial there. But actually, as of last week, no, not last week, maybe a couple weeks ago now, I made this site open source as well. So if you'd like to go and grill me on my terrible JavaScript practices, this is actually now available on our GitHub as well. So feel free to check that out however you see fit. We'll take a look at a demo of that in a moment, but we'll, just for a time, we'll kind of move on. So this the quick intro to graphs. So it helps to start with the like what and why of graphs and using graph databases. And when we're talking about graph databases, we're not really saying replace your SQL database with a graph database. SQL databases are here to stay. They have a very solid place in the tech world, and I don't think that will ever change, or at least it won't change for quite a while. They're very good at these like sort of single record lookups, and being able to quickly pull these sorts of records from either or entire tables even, depending on what you need. They're like the workhorse there. But they have an unfortunate name being called relational databases, because that's actually where we see their like weak point, is that whenever they need to be concerned with the relations that exist within data, the queries that are required to obtain that information can get quite complex and sometimes can just not be feasible at all. In a graph database, you store data as sort of these nodes, and then you persist the relations that exist between the nodes. And so we're kind of looking at a comparison here of like a product data set. And we're seeing that on the right here, we've got our products and then maybe how they're linked together. For example, if they're the same type of product, maybe they're all computer products, or even more interestingly is maybe these products were purchased together. And so we can start defining additional information about the co-purchasing behaviors for users and their relations to our products. We've seen things like this, for example, for like Instacart. They have a data set they made available, and we model it as a graph to show potentially you can show the relation between these nodes as the aisle that they're located in the grocery store. So when the Instacart shopper goes into the store, they now have the most efficient layout possible for them to collect the products. But of course, more interestingly is typically figuring out how they're related so that we can either recommend them to users or just try and determine like which products aren't that popular or valuable in the grand scheme of things. There's a bunch of other use cases we'll look at for this as well. But the main takeaway here is that we want to make these relations a first-class citizen in the database. We want to actually persist the relations that exist within the data. And this sort of graph structure here is also the foundation for AI and ML models. If you take a look at any basic neural network, this is a graph. You can't make a neural network without basically just drawing a graph. And we have seen the machine learning world sort of start taking this idea and running with it. And this is where we get into this graph neural networks. And we'll take a look at some of that a little bit later on as well. So just a quick sort of rundown of graph databases. Simply put, it's going to be a collection of nodes and edges, or just more so for what the graph is. As I already mentioned, naturally describing relations that exist within data. And the big benefit of using this versus some other sort of database is that the complexity involved in normally doing some of these individual lookups, like if we take, for example, here, one of the nodes on the right, this is an example of like a supply chain use case. So we're seeing what it takes for us to go from manufacturing to basically the doorstep of the consumer. This could mean it goes to a warehouse first, a grocery store first, a shopping department, or maybe somehow we're just concerned with logistics of getting it from basically the manufacturing or warehouse placed right to the door of the customer. But in order for us to go from one node to another, in some databases, this can mean 10 plus joins easily, just because we have to get, we get one row, we get its maybe a foreign key to get to this other one, we create this sort of like temporary table in the meantime so that we can now have all the information that we actually need from the single document. This is sort of that benefit of using a sort of document store versus a table. And the complexity of this really adds up when you actually want to do things like analytics on this data. I mean, whenever we start getting to things like fraud detection, these can be huge, long-running queries that just eventually become not feasible with some relational databases. For example, with fraud detection, a nice example I'd like to give as far as use cases go has to do with this. There's a thing called circular ring detection, where you want to see if a user submits a transaction from user 1 to user 2, and then that transaction goes from that same amount or some split amount possibly goes from user 2 to however many users. But the end result is that an actual ring form, a circle forms that goes all the way back to user 1. And the nice thing about having a graph database, especially if it has a decent visualization tool built in, you can run this query, and the end result is you actually see a physical circle form. And so you can run a graph traversal that actually does this over a very large amount of data and can return in a reasonable amount of time. And then you actually see a bunch of circles show up on the screen for this user. And that might indicate, okay, this user, this is more than just a coincidence now. This is something that we need to investigate further. And the way that you do this and the way that you support these sorts of things is by having these built-in graph algorithms, such as like k-pass, shortest pass, things like community detection, and even PageRank can be considered sort of an algorithm for graph databases. Other use cases, supply chain management, sort of briefly touched on. Recommendations, we'll look at a bit more. Customer 360 is a really, really popular one, connecting your users to all their other sources of information that they may have within your enterprise. That can be really, really valuable. And then the really nice, straightforward use case comes with network management. You can map out a physical, enterprise network, and then you can go one step further for intrusion prevention, or even doing just raw management activities, such as evaluating your network, doing, testing and balancing, and even sort of tying into the next one, risk assessment for what happens if this node goes down. What do I do? And then we've even seen people develop applications on top of this that are in charge of upgrading their infrastructure, making sure firmware is up to date, and actually rolling out these patches. And then risk assessment sort of ties into a lot of these others here, but in general, just this sort of this financial industry being able to leverage the connections within financial data. So that's really all I'm going to cover on the graph database side. If you'd like to learn more, definitely check out some of the other resources that will come up. For us, for this demo, this is sort of our rough view of the combining the machine learning with our graph database. It usually is going to require some sort of data. You're going to have some pipeline or something for ingesting the data into your graph database. This can then have, for us, it has a GraphQL endpoint sitting on top that's actually serving the query information for our demo. And then we have our site sort of living outside of this. But next to our graph database, we have to have some sort of connection, some sort of pipeline that connects to our pre-existing machine learning ecosystem. And this needs to support basically all the popular frameworks and libraries that are available for doing machine learning. And this is really where we focused on right now, is bringing this to the cloud, but then also making sure that you keep doing the machine learning you're already doing and actually be able to leverage those inferences and the outcome of those experiments in your graph database. And we'll start taking a look at some more of the slices here as we go on as well. So what is a recommendation system? Simply put, a recommendation system or recommendation engine provides predictions to businesses or users. This can sort of range in how this is done based on the business need. And this business-driven point here is talking more about what makes a recommendation accurate and what makes a recommendation good can be somewhat different. Based on the business need, you may be able to provide a really accurate prediction, really accurate recommendation, but this may get skewed based on wanting to also provide more, business business relevant results. Something that might make the business more money, but somehow still has a high level of accuracy. That's like a whole other talk here, but it's always just sort of honorable mention, is that depending on what you do with your recommendations may skew what's considered good, bad, or accurate. The other thing that can really skew this is the data quality. So depending on the data that you have, that can really also just push you in the direction of which method you'll actually end up using. As we'll see, if you have data with really rich features and a lot of information to work with, you may be pushing more on that content-based side of things. Whereas it's very sparse data where you don't quite have enough information to be able to use content-based, you may need to take other approaches that help sort of like fill in the gaps that just don't exist yet. And then maybe either you sort of evolve to using a combination of a lot of these methods, or that's end up being the method that just continues to work good for you. And we'll dive into what I'm talking about there. The other honorable mention here is definitely the privacy and explainability. This is more of just a machine learning in general talk. And I'm talking about whenever you generate your machine learning model, making sure that you do it with user privacy and safety in mind. This article that I've linked here goes into a detail on the result of building machine learning using user data and unwittingly returning really sensitive user information, such as social security numbers, because even though it wasn't really used in wasn't intended to be used in the machine learning experiment, you can basically query the model that's being served and derive this information out of there, even though that was never the intent to make that data available. As it was used throughout the training experiment, it actually persisted in the model. So just sort of I think an article that's always worth talking about. And again, that's another topic for another time, but wanted to leave a mention here just as we're talking about recommendation systems. Typically, you're working with user data, so this is a really important thing to keep in mind. The recommendation system is usually going to be domain specific and will usually require a domain expert, but there are methods that help get around that. But based on the domain that you're working in, this may push you to use one type of implementation method over the other. And the three that we'll really look at are going to be content-based, collaborative filtering, and then there's sort of an in-between, a sort of hybrid approach. And then finally, we'll take a look at using graph neural networks. As I mentioned, there's a lot of domains available for the recommendation systems. Product-wise, we see this every day at things like Amazon, Newegg, Instacart. Whenever you add something to your cart and they make those immediate recommendations saying customers who bought this also bought this. Or when you're just looking at an item and you see that sort of row underneath showing you all the similar items, there needed to be some way to determine what was most similar to that item that you were looking at. And there's a lot of, a couple different approaches that you can take there. And I think, this really is the most common way that we see. And I'll follow up on that as we go through it, because I think that one almost translates the easiest to the sort of Netflix style recommendation. But then you've got things like jobs, which I think is pretty interesting. Like looking at places like Glassdoor, Indeed, these places where they get lots of textual information from users. They're going to get a resume that's chock full of valuable information that would help them be able to match you with companies that are actually looking for your skills. But depending on what you did or didn't include in their, they form, they have you walk through them, they need some way to evaluate what your actual skills are, and then also do the same with the company they're working with. They don't always get the best descriptions from companies, so they need to be able to derive the information that the skills they're actually looking for in a candidate, and sort of do this matching up. So sort of making a recommendation that, hey, you might actually be interested in this job, or hey, you might be interested in this candidate. Destinations, Airbnb, Maps, Kayak, these are things that might suggest places either for you to go or once you've arrived somewhere. For instance, like maps. A lot of times when traveling, the first thing I do is open up maps and look for a coffee shop. And now when I open up maps, it just sort of tells me about the coffee shops that are available, because it knows that's what I'm going for now that I've arrived at a new location. People, this is a like classic one, I think, recommending friends, recommending groups to join across all the various social networks. And then on the research side, this can be with the healthcare industry, can use recommendations for even things like drug discovery, recommending next steps, or recommending interactions of drugs to like continue the experiment, or even just making recommendations to healthcare professionals that are working with patients that hey, these are symptoms they're seeing. What are some potential places to start? And then on the citation side of things, where if you're citing papers that in your paper that you're writing, it may be able to recommend further reading for you. On the search side, at the end of the day, we kind of feel like PageRank really is recommendations. It's evaluating the large amounts of text, a website, and then determining how similar it is to a search term that you put in. This is, of course, Google, Bing, and all of these search engines use some form of recommendation as they, especially if they're making money off of the site that you're going to, they may recommend sites that are beneficial for them as well. And then on the entertainment side, this is what we're covering, where we take a look at things like Netflix, Xbox, Apple TV, all of these places that are recommending things for you to watch, either based on your watch history or based on just the content itself. And if you are unfamiliar with all this, and why, if you ever hear about recommendation engines, they're probably going to be talking about movies, that's because Netflix actually did a $1 million challenge to kind of challenge the community to create a machine learning model or a recommendation method that produced better recommendations for them. And this link down here at the bottom is about the sort of Napoleon Dynamite problem that arose at the time. So this was when Napoleon Dynamite was pretty new, and creating recommendations for this movie was difficult because it was kind of just a weird movie. And so it didn't really fit into some of the other boxes that sort of existed at the time. And so there was an outcome of that a new model available called Funk SVD that was actually sort of able to tackle this problem amongst other movies. But Napoleon Dynamite was, of course, the most popular movie at the time, and was an interesting case. So feel free to read more on that if you're interested. And so whenever you're doing recommendation engines, you can have this huge scope of things that you're working with whenever you're working inside of an enterprise. It's usually not as cut and dry as we'll look at today. This is from an article that I wrote on the who's who in data science, and taking a look at sort of the life cycle of data through large enterprises, and specifically what happens once it gets to the ML side of things. And so we're not really going to go into this. Again, just sort of a link to follow up on if you like. Our scope is more like this, where we have our customer, they're interacting with our application. Somehow this is getting stored in our backend storage layer here. And then we have some sort of recommender logic that's getting either passed right back to the storage, or potentially just presented to the user on the application side. Now we can take a look briefly. I don't want to spend a ton of time here, as I think we might be running low. So this is how you can get access to the Orengo Flix site. You can get access to it through our cloud platform, and we have these examples available, and then you can click on this demo button, and it actually gives you access to your own version of this running website. And then once you're here, like I was already pointing out before, you can do various sorting and filtering. You can switch between the recommendation methods here to get different recommendations based on the technique that we're using here. And if you did want to learn more, again, here is the AQL query that we used here, and then a little bit more information about that method, and then those links that I was talking about, including the notebooks that I'll have linked to here as well. You can switch between the different users, and then you can also get a little bit more information about the movie itself. So like the description of the movie, genre, language, And it's sort of sorted by the different genres. And you can also see a look at the graph visualization for why this movie was recommended. So we're taking a look here at the recommended movie is actually the Shawshank Redemption, this black node here. And the connection that it has with the rest of the users and movies are kind of shown here, where the users are the orange nodes and the movies are the green nodes. We'll take a look at an example of this in just a moment. But yeah, so feel free to play around with that if you like. That's really all I'll cover here. But just so you know, this is available and can be found that way. And the links are available here. Okay. So for that site, this is the rough stack that we used for everything. For the recommendations, OrangoDB has this built-in search engine called Orango Search, and we use AQL for all of them as well. This is our query language. On the content-based side, including with Orango Search, we used TF-IDF. We'll take a look at what that is in just a moment. And for the external to OrangoDB part, we use sklearn. And for the matrix factorization or collaborative filtering side, we use the Surprise and SVD library. And then finally, for GNN, we use PyTorch Geometric, which we have an adapter for, and Espert. On the back end, we use our Orango Graph Cloud, which I just showed you, as well as the Python Orango driver for all the back and forth communications here. We also have a built-in microservices framework called Fox, and we use a GraphQL endpoint service that's hosted directly on the database as well. And on the front end, we used Vue.js, Vuex, Cytoscape, and PrimeView. Okay, so for the first technique that we're looking at is content-based filtering. For content-based filtering, they can offer very personalized results. So that means that they can take the behavior that you've already done, and they can really generate a nice score. For example, when we're talking about movies, if you've watched a Star Trek movie, you may also have an interest in other sci-fi films. We'll just go like Star Wars for the sake of it. I know that that's not necessarily always true, but based on the descriptions of those two movies, you may be able to develop a really decent score that says there's a lot of similarity for Star Wars to Star Trek. And hopefully I didn't just lose everyone on the call right now. But this is the way that you can sort of start personalizing these things, because you're actually basing it on the actual content itself as well as the user behavior. And this does require some domain knowledge typically. As it's being based on content, you need some way of validating that these are actually relevant. And you do usually need someone that's familiar, in this case, familiar with movies. This can be something that either you actually put back on the user, you make this recommendation and you see if they say, hey, this was a good or bad recommendation. Or depending on the use case, if it's something like healthcare or something like that, where maybe you need a little bit more input from an actual domain expert. This can also be very fast, depending on the system that's being used to implement it. But I would say of the methods that we look at, this definitely has the potential to be slow as well, because if you have a large corpus of text that you need to evaluate for every recommendation, this can, and you're trying to do that on the fly especially, this can definitely slow things down. For us, we have this built-in search engine, and we can do some sort of almost like pre-processing for every time a document is inserted. So whenever you're doing these ad hoc queries, it's pretty quick. And this is also something that we looked at on the machine learning side. If you sort of do some of this up-to-date, machine learning tasks, in your own infrastructure, and you just keep your data up to date with those inferences, that's sort of like win-win. You get to do machine learning however you're doing it, and then you also get to make those insights valuable in your actual production database. And so any queries that are running are immediately being able to use this information to enrich the queries themselves. On the content-based side, just to summarize a little bit, I had this nice snippet here from a really nice Google course on recommendation engines. They also have some nice courses on just generally machine learning and stuff. So that's what this link goes to here. Content-based filtering uses item features to recommend other items similar to what the user likes based on their previous actions or explicit feedback. I just thought that was a really nice, concise way of saying basically everything I just said. So the really popular way that the best place to start when you're talking about doing content-based recommendations is TF-IDF. This is term frequency inverse document frequency. Basically, how often does a word show up in a document, and then how often does that word show up across all documents? And the reason that you would be interested in this is you want to try and determine the value of a word. And you spread up this sort of calculation across all the documents, because depending on what you're interested in, you may be searching for a term, and if that term happens to show up in all documents, that could either mean, okay, all of these documents are relevant, or in most cases that's not actually helpful if we just say all documents are relevant. So what other words show up that might provide value or proximity value to these words? So it attempts to rank all the words that show up across all of your documents. And so when you're doing searches for them, you can sort of start picking out the most valuable documents. This is the explanation of sort of the algorithm behind how you can generate this scoring. Most libraries and frameworks that you're going to use will have TF-ID built in. It's very, very popular. And so getting started with it is usually quite straightforward. Same thing with our Orango search. We have a TF-ID method, and you can pass through documents basically and get the score back. Very little effort on your part to get these things running. But the next step of that is something called BM25. We'll take a look at that in just a second, but I just want to point out that we do have notebooks for both of these. So the sort of like purely Orango search sort of side of things, and as well as the only using machine learning and sklearn for this other side. If you do want to dig into that, definitely check out these notebooks. We definitely won't have time to look into them today. But as I was saying, next steps is BM25. This improves upon TF-IDF, as a problem that you run into with TF-IDF is that if you do have a lot of words showing up and a lot of documents, all those words still get rated highly. There needs to be some way that says, okay, this word shows up too much, basically. And it is now devalued, even though it might have been considered a high-ranking word purely because it shows up across all these documents. There needs to be a way to determine, okay, this word is being used so much, it has lost value. This is what we call the frequency saturation. And that's where BM25 comes in. It's really like an evolution of TF-IDF. It also does things like consider the length of the actual attribute that it's viewing, or the document potentially. And while it is conceptually more advanced, as in it has a lot of other features that you can take into account, it's almost just as easy to use as TF-IDF. And so we have this also built into Orango search, and this is another one. Basically, anywhere you go, any library you're using is going to probably have support for this if it has to do with this text processing. And as I briefly mentioned there, this is sort of our approach for if you're doing machine learning, how do you actually leverage that inside of a graph database? So on one side, you have a movie or a user, and on the other side, you have movie or user. So what we're probably interested in is, for example, how similar are two movies? And perhaps we can just figure that out. Based on our content-based approach, we maybe take the description of one movie and the description of another movie. And we want to figure out how similar the content of these two are. And once we have this similarity metric, we want to actually somehow persist it. And so what we would do in a graph database is have an edge that connects the two that we actually store this similarity metric on. So as we're doing graph traversals, we can be taking the similarity metric into account as we go from one movie to the other. And perhaps if we hit a certain threshold, we say, okay, we're not going to continue down, we're not going to connect to that movie, basically. Or if we want, we have a director and we want to get all the movies that they have done that are similar to each other, because we really like that director, but we only want to watch, these types of movies that they have done. These sorts of things can really start to come into play when you're doing machine learning inside of a graph database. And the next method that we're looking at, and apologies, I just want to make sure I can get to the end here, so kind of like speeding through it a little bit, but we have collaborative filtering. Collaborative filtering, this is sort of the example that we were looking at in the demo here, is taking user preferences and generating recommendations based on the patterns that already exist within your data. So for us, we're looking at, well, the user we're interested in has watched some of these movies, And then there's a lot of other users that have also watched those movies. So what movies did those users rate highly? Because that's maybe a movie that we could recommend to our original user here. So on the far right in this graphic, we have Arthur, who has watched Tron, Cinema, Paradiso, and The French Connection. And then we have these other users that have also watched those movies, and they all collectively actually rated The Matrix highly. So this might be relevant when we're looking at a genre that's like similar to Tron here, right? So we might recommend Matrix in that situation because it has a high sort of collaborative filtering score for Arthur. And this has the benefit as well of being able to offer these recommendations with limited domain knowledge. It can do this because it's just using existing data. And so with sparse data, this technique is really, really powerful. For example, we're looking at a matrix here. This is why we kind of call it matrix factorization. One thing that we try and do is reduce the dimensions that we're looking at. This can be done in a number of ways, such as potentially generating this number here, 1 through 5, based on a couple different metrics. For the sake of this brevity here, we'll just sort of say it's like a rating. And if we look at user 3 and 4, we can see that they have a somewhat similar watch history, where user 4 has not seen the movie Babe. And so based on the fact that these users have similar watch behaviors, watch patterns, we might be able to guess that user 4 isn't going to really care for Babe either. As this matrix grows, though, you may actually end up seeing a lot of different patterns show up. This is going to get a little bit more complex, and answering that sort of question won't be as easy. But as you take in more data, it becomes way more accurate to say, to aggregate all the various user behaviors and start finding these different patterns that might even end up indicating that user 4 might actually like Babe because of a bunch of other movies they've watched and a bunch of other users that have similar patterns. So the more data you have here, the better. But it is able to work with very sparse data and still return results, which is really nice, especially when you first get a new user into the system and they may have very limited data to go off of. You can still start offering these recommendations. And most commonly, this is also combined with the content-based approach, because now you can say, okay, I've got some sparse data. I might recommend these movies. I'm now take into account how similar these other movies are. And I would say actually in the wild, you see the combination of what we call the hybrid approach of both of these techniques most common. It's really the better way to go if you can. And again, we have a notebook available here for you to dig into and see how we actually generated these recommendations. And then finally, I've got like 5 minutes left, I think, here. We have our graph neural networks approach. I think the best thing to do if you are sort of interested in learning more about graph neural networks, we have Sachin Sharma. He's one of our ML research engineers. He did a really great talk on GraphML, NVIDIA Tridon, and OranguDB. We actually partnered with NVIDIA as part of their Inception program to develop this sort of model serving and how we can integrate this. So if you'd like to learn more about that, check that out. It's a really decent workshop. It is a bit longer. This concept itself can be pretty deep topic. So I think it's a couple-hour workshop, but it goes in. There's a lot of takeaway notebooks that you have there as well. So be sure to check that out if you'd like to learn more there. The general motivation of doing graph neural networks, though, is sort of taking this sort of network that we're working with, this graph that we see in traditional graph databases, and somehow encoding it so that it will work in an embedding space, as this is typically where you're seeing neural networks working. And so we go from our sort of what we would say in this situation, like an OranguDB graph, right, a property graph, and how do we get this into this embedding space so that we can start doing some of these clustering activities. This is really the big goal here, is if these nodes are still aware of their surroundings inside of this embedding space, and then we can identify these clustering tendencies here, we can actually do things like link prediction to say, okay, well, technically in our property graph, they live far apart. But as we began mapping them into our embedding space, and we do this based on their neighborhood information, we see, oh, actually, we have this cluster. So maybe we can determine that these are all the same category or whatever activity that you're working on. So this is like the most simply put way of this is really what we're wanting to do. We want to take our existing data, map it into a graph embedding space, and then make sure that we are preserving this information so that we can actually make use of it in our production applications. This is an example of some of the challenges here. I think really the one to focus on here is in the middle, where when you're working with this, you need some way of having a fixed number of neighbors. In our property graphs, this has way fewer restrictions. Way fewer restrictions like this. So you may have something more like on the right. And how do you form your data? How do you map your data so that it will work like this? And so this is where some of our efforts have come in. We've developed adapters and libraries to help going from our graph database to whatever tool you're using much, much easier. And so this is really where on the Orango ML side, we've seen a lot of development effort happening. And this is why we've really put sort of our whole faith behind launching our machine learning platform. For the movie recommendation side, we did do this link prediction task. So basically, we're just trying to predict what rating a user would give a movie. This sort of sounds simple, and but at the end of the day, it's just like sort of one of those bigger topics that graph neural networks are actually able to solve. I don't want to say easily, but it's a great problem for a graph neural network to solve. And again, got a full notebook that runs you through how we do all of that. And yeah, as we sort of already have looked at, this is sort of the ecosystem that we see happening. You're doing your machine learning. You have your machine learning ecosystem of whatever pipeline you're already using. And now you need to figure out how to get this data back into your actual knowledge graph, into your graph database. This is that sort of ecosystem I'm talking about. We have these adapters for NetworkX, DGL, QGraph, Orango RDF, the Orango ML pipeline, and the PyTorch geometric adapter. And we just launched what's called the Fast Graph ML, which I highly recommend checking out as it's a low-code framework for those getting started with machine learning. All of this is available through our GitHub as well. And this is sort of I think I'm going to run out of time, so I don't want to go over too much here, but this is a quick sort of overview of how you might use your existing machine learning with a graph database, and specifically doing this model serving activity with the NVIDIA Tridon server. So sort of across the top here, this sort of like top shape, we have our database, our application, and then somehow our inferences that are being generated through either being just pulling the model from this model repository or potentially doing active machine learning activities. And these inferences are constantly being synced back and forth to the database. And this is possibly being triggered either through some front-end application or some back-end tasks that make sure to keep any up-to-date inferences available on the database. And then as you see here at the bottom, once we have these things being stored in OrangoDB, we can actually use our query language to traverse these embeddings that are actually being stored. This is a small slice from the talk that Sachin gives. So if this seems like you'd like to know more, definitely check that talk out. And as a final takeaway here, here's a lot of the resources that I think if you're just interested more on the not just on, but on the recommender side of things, these are some really great resources. These pictures are all links as well. So a great book on practical recommender systems, a great course from Coursera, that Google ML course that I was talking about. And then this, if you are interested in that one that sort of won the prize for Netflix, this is its starting place, SVD, singular value decomposition. And Steve Brunton had some really awesome videos, and this links to a really great playlist that I found for kind of walking through these concepts. And if you'd like to learn more just in general about the Netflix and matrix factorization, there's a link on the left there as well. Yes, so I think that's everything that I have. Here's all the links to all the notebooks, as well as the ML repository and the cloud as well. Yeah, so I think now I will take questions potentially if I haven't eaten up the time.
Awesome, Chris, that was a wonderful presentation. I have learned tons and I took a lot of notes too. We do have a couple of questions, so I definitely want to take a little bit of time for that. So let's look at the audience questions before, because I warned them that if they wouldn't post questions, I would have my own. I have my own to start with, because you mentioned Star Trek and Star Wars. So which camp are you?
Definitely Star Trek.
Okay, so we can be
day.
friends.
Yeah.
That's good.
Yeah.
I'm very glad. All right, let's start with an audience question. Orsalia is asking, what is the hardware requirement for establishing a graph database? Could we create it in a Hadoop cluster, for example? How could we imagine it in terms of information storage?
Yeah, so for a graph database, like I can speak from our side of things. Like, to get a graph database running, you can run it on really any infrastructure. I don't want to sound too brand there, but we support all the Linux distros, Docker. We have a K8 Kubernetes operator. Yeah, whatever platform you're using, you can run this on. And on the scalability side of things, this is important, as we do have a cluster architecture. So this is the big thing that we have focused on as our graph database. Sort of the way it segments things allows you to scale vertical and horizontally to whatever way fits best. So you can spin up a multi-node cluster to your heart's content. I hope that answers.
Awesome. Yeah, I hope it answers the question we might see in the chat or not. Another question by Sebastian Klein. What do you think of factorization machines as a recommendation algorithm, especially in comparison to matrix factorization?
Factorization machines. I honestly, I'm not as familiar maybe with that term. So I don't know I'm gonna have a great answer for that. So apologies. It may be something I'm aware of. I'm not familiar with that term though.
Maybe you can meet Sebastian in the chat later on, and you can figure out
or
together.
feel free to follow up with me on all those links that I provided as well, Twitter or Slack or however.
I'm pretty sure they will. Question from Francesco: how big can the graph be? Does it need to fit all in memory for these calculations to take effect?
Cool. Yeah. No, that's honestly, I think, kind of ties in that other question, is the ability to scale. For some databases, this is a requirement that basically it has to be in memory. For us, no, we do have this idea of like indexing, so you can use indexes as you traverse. But in general, our graph traversals don't require that you load the entire graph in. There's lots of concepts for ways to reduce the amount of data that gets put into memory. So yeah, so I would say no, it doesn't require that. And yes, you can definitely scale out. Working on currently right now, I'm working on a 1 terabyte benchmark right now actually for us. And we certainly don't need 1 terabyte of RAM to do that. But I know this is something that some vendors require. So.
Alrighty, let's take one more, and then we need to skedoodle, I think. But mathematically speaking, what is a commonly used distance measure identifying potential recommendations that appear to be close to my previous choices? In the sense, how do you define relations or distances between words in such a multi-dimensional space?
Yeah, so I mean, depending on what you mean by that, I think the outcome of that is usually we're looking for some similarity metric. I think there might be another question there that I'm missing, but as far as yeah, I think I'd have to get a little bit more info. But in general, like if we're talking about the similarity score, right? This is going to be potentially either ranking the words that exist within the text itself, or just assigning a ranking value to the entire document. Yeah, I think this is usually represented as a distance metric. So if we're thinking about something in like a Euclidean space, we're thinking about how close is this word to the other word in this dimensional space. And so that distance metric is a lot of times just basically what we're talking about when we say like a similarity metric. I hope that, yeah. Definitely follow up with me on that one. I think that's a bigger question there.
Perfect. So the person asking the question, follow up with Chris offline or in the chat later on. We have to close here, but we'll be back in this track in just a little bit, learning more about AI in a minefield, learning from poisoned data with Jonathan Azaria. Thank you again, Chris, and thanks everyone for watching.
Thank you.